Alright gang, here we go. This is for Physics, Unit 7. We're finishing up Part 1 here. We're going to talk about different ways to measure the motion, or simple harmonic motion. So in the previous video, we specifically focused on oscillating around a spring, right? We talked about a spring motion with some weight attached to it and the spring oscillating back and forth. And we kind of defined Hooke's law and simple harmonic motion, what it means, why it's important, what kind of things we can glean from it. And then we kind of moved into talking about restoring forces. And specifically with restoring forces, we were looking at a pendulum, right? And we had this pendulum that was going back and forth like so. All right, and from there, we can also assume, and we know that restoring force is really measured by Hooke's law, right? And Hooke's law gives us something like this: Fe equals negative kx. All right, and so this is our restoring force. This is the thing that's trying to get it back to equilibrium. All right, and so try to keep that in the back of your mind as we move forward. We're going to specifically talk about period and frequencies of a simple harmonic motion. Okay, and we're going to focus on pendulums because it's kind of the easiest one to recognize and most interesting. But we'll take a look at the oscillating systems that use springs as well. Okay, just I wanted to recap a couple of terms that we've learned in the past, but just make sure that we're all on the same page here. All right, amplitude is the maximum displacement from equilibrium. Now notice that we're using pendulums to define all of these, but really we could easily use the mass spring systems. It's not really a big deal. Okay, now the the amplitude is just the maximum displacement. Okay, so notice that for a pendulum, right, so this dashed line is that equilibrium point, and there's the ball, it's the dashed line ball. This max displacement from equilibrium, that is your amplitude. Okay, so that's, for a pendulum, notice that this value, we're actually measuring it based on the angle. Okay, so we're going to measure it in either degrees or radians. Primarily, we're going to focus on degrees, but technically the SI unit is radian. All right, and then, but if we were using a mass spring system, remember we had like, I should have drawn, there's your spring and there's your mass, right? When you measure, if this was the equilibrium point, we'd be measuring this distance and this change in x, and it would be in meters. Okay, now, two new ones, or not new, but the ones we want to focus on a lot here is period and frequency. All right, period is defined as the time it takes to complete a full cycle. All right, so the time it takes to complete a full cycle. So, and a full cycle would be from one point back to its original point again. So we're starting on one end here, we go out, and then we come back to this original point. So that would be one full cycle, and the amount of time it takes to do that would be the period, and this is measured in seconds. All right. Now, very closely related to that is the frequency. The frequency is defined as the number of cycles per unit of time. Now, specifically, we're going to use seconds because that's the SI unit for time. All right, so it's the number of cycles per second. All right, so notice that the unit for it is per second. Remember, anything raised to a negative exponent is where that unit goes on the bottom. So this is per second. This is per second. And specifically, instead of just saying per second all the time, we also call it hertz. Hz for hertz. Now you notice that our period is in seconds, and then our hertz is in inverse seconds. So really, our period is equal to the inverse of our frequency. Because if we turn our frequency upside down, then our seconds are back on top, and we get our period. Now this is really important because in my humble opinion, period is easier to calculate, right? We can just kind of say, all right, we're going to watch a full motion and then run a stopwatch. When it reaches the other end, that's how much time it takes. That's your period, right, for one full cycle. Okay. And then to get the frequency, you just flip it over. You take the inverse. 1 divided by whatever your period was, that gives you frequency. All right, so we could always write it like this as well, where your frequency equals 1 over the period. So it's kind of nice that you can kind of flip-flop between the two of them. All right. Now, period's also cool because we can also use the length and the acceleration due to gravity to calculate the period of a pendulum. Okay. Now, this only works for simple pendulums, all right? Small angles. Remember, we talked about Hooke's law only works for small angles on our pendulums. Springs, totally different ballgame, but for pendulums, it has to be within a small angle range. Less than, specifically, it works best for less than 15, but like 20, 25 is also fairly decent as well. But we're going to focus on less than 15-degree angles, all right? Now, the period, the capital T, depends only on the length and the value for the acceleration due to gravity. This should be a subscript G, acceleration due to gravity, like that. All right. notice that the mass of the object does not affect the period, and that's because all masses accelerate at the same rate. Okay, it's pretty wild. All masses accelerate at the same rate, so it doesn't matter what the mass is. So if you have a pendulum, your period is going to be the same whether you have like a 2-ton car at the end of your pendulum or a marble at the end of your pendulum. It's the period of it is going to be the exact same. Now the energy that it carries, that's going to be a totally different beast, but the period, that back and forth motion, how long it takes to do it, is going to be the same. Kind of wild. So here's your formula. T equals 2 pi times the square root of the length of your pendulum over the acceleration due to gravity, which is always 9.81. All right. And so you can also see that if you have a pendulum set up and you take that pendulum, all right, on Earth, and say on Earth it has a 2-second period, and then you take it to the moon, you pack it up, you ship it off to the moon and unpack it and run your pendulum, the acceleration due to gravity is a lot smaller. Now because of that, you're dividing by a much smaller number, so your period will be much longer. When a lighter gravity, it will take a lot less time to be able to go back and forth. And that makes sense because that means our restoring force would be less. Remember when we talked about restoring forces? The restoring force is the force that it takes to bring our pendulum back to equilibrium. Okay, and it restarts, and that's kind of what keeps it going in that simple harmonic motion. So if our restoring force is less, that would produce less acceleration, so we'd go slower. Okay, and then vice versa. If you take it to like Jupiter, you take it to the moons of Jupiter, and then or not the moons of Jupiter, you take it to Jupiter itself, and you set up your pendulum and go, the acceleration due to gravity is going to be a whole lot higher. Okay, so that pendulum is going to go a lot faster because it's divided by a much bigger number, so your period goes down. Okay. We also can have a very similar thing for a mass spring system. Okay, so same sort of idea, just not a pendulum, just that mass spring, simple harmonic motion. Okay, notice the formula is almost exactly the same, only the difference is we have the mass instead of the length, and then the spring constant instead of the acceleration due to gravity. All right, so the harder your stronger the spring, the bigger your K value, the more it's going to accelerate, and therefore the faster you're going to vibrate, or the faster you're going to go back and forth. So you're going to have a much shorter period or a faster, much higher frequency. All right, so here we go. What is the period of a 3.98 meter long pendulum? What is the period and frequency of a 99.4 centimeter long pendulum? So this is pretty easy. We're just going to take our formula that we had before. That was the T equals 2 pi times the square root of L over acceleration due to gravity. All right, and we're just going to plug in our values. So we have 2 pi times the square root of our length, which is 3.98, divided by acceleration due to gravity, which was 9.81 meters per second squared, and this is in meters. All right, so we take all that guy, we say 2 times pi times the square root of 3.98 divided by 9.81. We get 4.00, okay? And then this is the period, 4.00, so the units is in seconds. Now the next one here, same idea. We've got our period is equal to, and I'm not going to rewrite this equation, but it's the same thing. But, so we have 2 pi times the square root of our length. Now our length is in centimeters, so we got to change that. So that would be 0.994 meters. All right, over the acceleration due to gravity, which would be the 9.81 meters per second squared. All right, so we take 2 pi times the square root of 0.994 divided by 9.81. We get 2.00000, so 2.00 seconds. Okay, now notice that our pendulum here went from being 4 meters to only being 1 meter in length. And so notice that the period, instead of it getting 4 times less, it only got half as less. And that's really because of the square root thing that's right here hanging around on our length. Okay, so it had, took the square root of that factor that was involved with it. All right, then it asked what is the frequency of this? Well, we know that frequency is equal to 1 over the period, right? We established that earlier. So therefore, we take 1 over 2.00 seconds. So we get 0.500. And our unit for frequency is hertz, all right? So there's your answers for those two questions, all right? And those are the same things there, all right? Now, next one it says a desktop toy pendulum swings back and forth every 1.0 seconds. How long is this pendulum? All right, so we need to find the length. So we got to do a little bit of rearranging here. So we got our period is equal to 2 pi times the square root of L over acceleration due to gravity. All right, and we're going to solve for our length here. All right, so we're going to divide by 2 pi on both sides. So T over 2 pi is equal to the square root of L over AG. Okay, and then we're going to square both sides. So T over 2 pi squared is equal to L over AG. All right, then we're just going to multiply both sides by AG. All right, acceleration due to gravity. And so therefore these guys will cancel, right? And you'll be left with your length is equal to your acceleration due to gravity times T over 2 pi squared. All right, so let's see what we get here. Let's see if we get 0.25. So 9.81 times, and our period is 1 divided by 2 pi squared, and we get 0.24849. Okay, and we want 2 sig figs because its period is only 1.0 seconds, so we get 0.25, and since we did everything in SI units, our L is in meters, so 0.25 meters. All right, pretty easy. Okay, let's try another one. What is the free fall acceleration at a location where a 6.00 meter long pendulum swings exactly 100 cycles in 492 seconds? All right, so same idea. Our period is equal to 2 pi times the square root of L over AG. All right, but it asks for the acceleration, so we needed the acceleration due to gravity. So now we're going to solve for the acceleration due to gravity. All right, so same sort of idea here. We're just going to jump the gun here because we've already solved for parts of this. T over 2 pi squared is equal to L over AG, right? This is exactly where we were just the previous slide. All right, but now we need to solve for acceleration due to gravity. All right, so there's lots of ways you can go about solving this. I'm going to simply multiply both sides by acceleration due to gravity. So we're going to get the acceleration due to gravity times T over 2 pi squared is equal to your L. But we need acceleration due to gravity by itself, so we're going to divide both sides by that, by T over 2 pi squared. So you get acceleration due to gravity is equal to, and it would be L over the quantity T over 2 pi squared. And we can rearrange this to make it a little prettier. So it would be L times 2 pi over T quantity squared. Right? So the acceleration due to gravity would be equal to, now our length is 6 meters, 6.00 meters, right? And then 2 pi times our period, or divided by our period. Now the period, remember, is defined as how long it takes to do one cycle, right? So we need it in seconds, so you take 492, right? So our T is equal to 492 seconds for 100 cycle, because we want to know how long does it take to do one cycle, right? That's our period. So we're going to take 492 divided by 100, so you get 4.92 seconds. So that's our period, 4.92 seconds. All right, and we're going to square all that guy. So it would be 6 times 2 pi divided by 4.92 squared. And I got, this has 3 sig figs, all three sig figs, so 9.79 meters per second squared. Is that what we got earlier? It is. Hallelujah. All right, so that's how you'd find the acceleration. We'll do that in a lab together. All right, let's do one more. We're finding the spring constant. So this is essentially exactly the same thing as what we just did. All right, only we're going to finally be using that other formula, T equals 2 pi times the square root of the mass of our thing over our spring constant. All right, we want to solve for that spring constant there. So we're going to do some math magic. Okay, so T over 2 pi quantity squared is equal to mass over K, right? Multiply K both sides, divide by that. So our K is going to be equal to mass over T over 2 pi quantity squared, and that's going to be the same thing as mass times 2 pi over T quantity squared. All right, So that means we can plug everything in here. So our mass value here is 1 kilogram, so 1.0 kilograms. That's nice. All right, and then our period, well, they just give it to us straight up. That's nice. So that's 2.0 seconds, and then over 2 pi here. All right, and square that. All right, so you take 1 divided by, oh, why did I do that? You guys are, oh, I did this one, didn't I? I went and solved it, whatever. 1 divided by 2 divided by 2 pi squared. And we get 9.87. And it's newtons per meter because it's the spring constant. Oh, and we want everything in 2 sig figs, so it would really become 9.9 newton per meter, which is exactly what we got up there. Perfectly done. Well done. That's it for part 1. It was kind of a lengthy part there, but that's all right. Lots of new things to learn and stuff like that. Do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.